Welcome to episode 2 of Explainercast. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. This is a second part in probably a 2-part series, although we'll see, it might turn into a trilogy, of Sailing Explained. And I don't know, we had such a good time with episode 1, we just didn't get through even half the material we wanted to cover for the second part.
Yep. All right. Yeah, I figured we'd start with kind of a recap since we explored a lot of things, but we didn't really maybe establish the full foundation. And then we can get back into kind of all the interesting kind of side pathways in understanding how sailing really works. So do you want me to start with that?
Please.
Okay. So essentially, the sailboat is a relatively simple machine. You have some type of floating hull, the boat itself, and its job is to stay on top of the water. And then it has some mechanism for directional control. And so we talked about two pieces of that. One of them is called the keel, which is essentially something that sticks down below the hull into the water. And think of it as long and skinny so that it makes the boat want to go forward or backward, but primarily forward in a straight line. And then there's usually some type of directional control, like a rudder, that can be used to to steer the boat and have it point in a different direction, and then it wants to go straight in that direction. And so now we have that boat, that hull with the keel and the rudder, but no power source yet. And so this being a sailboat, the sail is going to provide the power, and essentially there's going to be a mast, a vertical beam that is attached to the hull and sticks typically straight up in the air. And then extending backward from the bottom of the mast or near the bottom of the mast is something called a boom. And that forms two sides of a triangle. And then the sail is essentially pulled taut, typically a piece of fabric in a triangular shape. And it's pulled taut between the mast and the boom, kind of filling that triangle with the fabric. And typically the sail is oriented toward the back of the boat, but off to the side to a certain extent so that the wind can hit it kind of on an angle. And then that sail is going to essentially curve the flow of that wind toward the back of the boat, which will then propel the boat forward. It does also result in pushing the boat to the side. And because the sail is up above the hull, it's going to kind of lean the boat over. And so the keel is going to prevent that side force from causing the boat to drift sideways. As long as we have some speed, the water flowing over the keel will force us to go in a forward direction. And then to counteract the tipping force, because we're pushing up on the mid part of the sail from the side with the wind, there's typically a heavy weight attached to the bottom of the keel that pulls the boat back upright as it leans over due to that force from the side. And so that is all you really need to have a basic sailboat that can sail in almost any direction except straight into the wind. And I think we'll talk a little bit about how we make progress into the wind on a diagonal. And then there are all kinds of optimizations that can be applied. And we talked about some of those last time, including lighter weight mechanisms instead of a heavy keel. We talked about dagger boards and hydrofoils and so forth. And so we'll probably get more into that later in the episode. But I guess with that as our overview, where should we go next, Dave?
Well, first I think we should point out that some of these words have a weird origin. Like, for example, the word boom is named after the sound your brain makes when it explodes when you realize that the sail is actually the same concept as an airplane wing.
Exactly. Yeah, and then keel, of course, maybe you keel over later, but...
Yeah. Boom, keel. Okay, got it.
Yes.
I think our audience is quickly learning who's the expert here on this particular topic.
Yeah, we'll have to trade roles on a future topic for sure.
Let's talk about direction. You said that you can go almost any direction in a sailboat.
Yep.
Except directly into the wind. So you kind of have like 359 degrees of options. Oh, and also you should mention you can't go straight up.
Yeah, that's true. I mean, we can't levitate per se, at least not indefinitely.
Yeah.
We can.
I guess that's not true. Yeah, you can go up a little.
That's right.
Once in a while.
But yeah, and I would say 359 degrees is a bit of an overstatement because we're going through the wind, and so as you point more and more into the wind, that wind is essentially blowing you back. And so the practical result ends up being that a high performance sailboat can maybe get to within about 30 degrees of upwind. So think 2 o'clock or 10 o'clock on a clock face if the wind were coming from 12 o'clock. More typical would be or maybe that's maybe even probably about 2 o'clock. I guess it would be a 45 degree, and that's probably about where you're at. Yeah, I guess actually 130. Yeah, so maybe the 30 degrees, like a really efficient boat maybe could be all the way up like at 1 o'clock or 11, but more commonly it would be 130 or 10:30, about 45 degrees.
Okay, so 45 degrees is about as far as you can go into the wind, and this is counterintuitive, I think, because most people, myself included, who have adopted the bed sheet notion of sailing, where you're sitting in a trash can holding a bed sheet in the air, or an umbrella, the parachute mode. It's very counterintuitive to think that you can actually move an object into the wind when the wind is your only source of,
and that's true. It's
that propels you.
And this is where there's a couple things to think about, and one of them is that while the wind is the only source of energy in this, it's really the shear of the wind relative to the water. So it's that there are these two different media that are moving in different directions, and we're exploiting the difference between them to extract energy. And intuitively, this does rely on the efficiency of two components. One of them is the efficiency of the boat in the water and that keel in allowing us to go straight with very little friction or drag, slowing us down. And so the result is that if we take the sail away for a second, imagine we've got this hull, this boat sitting in the water, we've got this keel, and the boat is sort of really like slippery in the forward and backward direction and really obstructed in the sideways direction.
Yes, that matters.
So imagine like you're trying to dock the boat or something, and it's just a few feet away from the dock, and you're trying to pull it straight sideways, against the dock. That's going to be very difficult, and it's going to move very slowly.
By design.
By design. It's not intended to go sideways. That's right. On the other hand, if you were trying to walk the boat, say, forward along the dock and propel it in the direction that it's facing, you'd find that you have to coax it to overcome its momentum, but it actually glides quite efficiently. And so, so it's very efficient forward and backward, and it's very rigid, essentially, to the side due to the action of that keel in the water.
And Shane, I've heard a good metaphor for this is like an ice skate.
Oh yes.
You put an ice skate on ice.
Yep.
And you can slide it back and forward and back, very smoothly. But then when you try to drag it left and right, it resists.
That's a great metaphor. And reality is you can make a boat using that technology too, and make an ice boat, and they can go very fast because of that.
Oh, cool.
And so just thinking about that boat now. Imagine, so we push straight sideways and it very slowly kind of concedes to the side. But imagine now you were to apply your force, you're pushing on it kind of on a diagonal, like say 45 degrees between straight forward and straight to the side. And what do you think would happen if you did that, Dave?
Yeah, and this is where the ice skate metaphor helps me, because I think, okay, I'm pushing on my ice skate. Okay, so depending on what angle I'm pushing at it on, the ice skate's gonna place the ice skate directly in front of me.
Yep.
And then I come at it with a fingertip.
From behind.
At a 40 from behind, and I press on it.
Yep.
And the ice skate is actually going to slip backward toward me, right?
Well, sorry, I guess I was picturing it differently. So, yeah, maybe let's change it and let's put a person in the ice skates even, and let's orient to them. So like we have a person in the ice skates, they're facing forward, and then tell me where, think about as you push them from different from the side or from behind or from the front, and think about, and explain what would happen.
Well, yeah, so let's work our way around the clock. Yep. So I'm facing them, they're facing me, and I just push them away from me. They're going to go away from me.
Exactly.
Easy.
Yep.
Right.
Yep.
And if I get on the back side of them and I push them away, they're going to go away from me.
That's right.
But and I think no one's confused about that.
But that would be equivalent of like dead downwind sailing. If you're straight behind them on 6 o'clock and you push them towards 12 o'clock, they're facing towards 12 o'clock, they're going to go straight that way.
Right.
Okay.
And this is actually not even the fastest kind of sailing that there is. It's dead downwind. Right. But then things get really weird when you stand slightly behind them and off to the side.
Right.
and now I reach my arm out just as straight as I can, and I push them at a 45-degree angle.
Right.
And this is where my intuition fails me a little bit, but I have this idea, like let's say I'm standing behind them to their right. We're both facing in the same direction, and I reach out and I push them at a 45-degree angle.
Yep.
My intuition says that they're going to go backwards, but that could be wrong. I don't know.
Yeah, so let's push them from like behind and to the side.
Okay.
You're going to like put your hand on their shoulder, kind of, you're one step behind and you're one step out to the side, and you're going to push.
And I'm rigid here. I'm like standing in spike shoes.
Yes,
that's
right. You've got grip
not on
in
my
this
own
case.
ice skates.
Yep. And they're going to brace themselves. And so actually we think about this. The first thing is actually if you push like on their shoulder, they're going to have to brace so they don't tip over. Because if they were perfectly balanced and they didn't adjust, you'd actually knock them over. And so that's why we have our keel to keep us upright. But the next thing that's going to happen is as you push kind of on that diagonal, that ice skate's going to prevent them from slipping sideways. If they were just in like tennis shoes, they would slide, straight away from you on whatever diagonal you're pushing. But with the ice skates on,
but they're not.
They're not, exactly. With the ice skates on, the ice skate is going to resist the sideways component of that force you apply, and it's going to yield to the forward or backward component of the force that you're applying. And so you end up decomposing that force into these two perpendicular components, and essentially, the ice and the skate are going to interact to resist that sideways force, and then along the direction that they're facing, they're going to glide. And so
they'll go forward in this case.
They'll go forward. That's right. And if you're straight behind them pushing, all of your force is propelling them forward. As you move to the side, it's only the sort of the portion of your force that is oriented in the forward direction, that component that is going to propel them forward, and more of that force is going to be resisted as a sideways force as you move all the way to where if you were straight beside them pushing, on one shoulder, directly across their body. And if you were to continue forward, you would start to push them backward. So the range of useful force that can propel them forward has to be somewhere on, from directly to the side to straight behind. So essentially there's half of the, of the compass that works for us there. And the closer we get to pushing straight to the side, the lower the impact of the force is for their forward direction, and the more it's just pushing against that sideways resistance. But if there's low enough friction, and the ice skate's a good example because it's very low friction, even a force that is mostly sideways but has a little bit of forward component can still accelerate them forward until that force is equal to the resistance caused by friction or wind resistance, due to their forward velocity.
And that has an additive effect because we're talking about wind that is just a constant bombardment imparting force over and over. It's not like ice skates where I can give you one push and then you're off.
That's right.
It's a perpetual
force.
Hitting. All these air particles are just slamming into the side at that angle.
Yep.
And so it continues to impart more and more force, which of course force is mass times acceleration.
Yep.
And so the mass is constant and you're actually applying an acceleration.
That's right.
So even though let's say the wind is only traveling at 5 miles an hour, with a sufficient buildup of those 5 mile an hour particles hitting the sailboat over and over and over, it will eventually exceed 5 miles an hour until it hits its essentially terminal velocity, where all the other resistance on the boat, friction and other things, will eventually stop, prevent it from accelerating anymore. Is that right?
Yeah. So if we were going straight downwind, then as you got to the speed of the wind, then essentially, if the boat's going the same speed as the wind's no longer able to provide any force because you're neutral to it. So that's why
But at an angle, that's not the case, right?
That's right. So as long as there's some angle, then you'll have an opportunity to extract some amount of energy from the wind. And so we may want to talk a little bit later about that as we talk about how to go fast downwind. But thinking just a little bit more about this construct, you're absolutely right. The wind is going to give us an opportunity to continually apply a force. And that actually is super important because there are continuous resistances to our travel in this boat. There's resistance provided by the water as the boat moves through it. There's also air resistance because the boat is moving through wind. And as the boat accelerates, it actually incurs what's called a relative wind, which is, if you picture that 5 mile an hour wind, say, blowing kind of crosswise across the boat, say from side to side, if you manage to get the boat going, 5 miles an hour forward, now you actually have the sum of the 5 mile an hour crosswind plus the 5 mile an hour headwind. And, if you do the math, that's going to be like 7.5 miles an hour or something of wind on a diagonal, which is called your relative wind. And so as you increase your speed, you increase into the wind, or at least crosswind, you increase the relative wind, and that ultimately provides more resistance to motion, which needs to be overcome by that continuous force.
Got it.
So the shape of the hull and its efficiency in the water is key, because that allows, even if the sail isn't pulling the boat straight forward, but the sail is imparting this kind of diagonal force on the boat can utilize that forward component. And so as long as there is a non-zero forward component and it's equal or greater to the amount of resistance due to the current speed the boat's traveling, the boat will accelerate or maintain its current speed. So that's the first half of it, but we still needed a force that was moving the boat forward. If the force is coming from in front of the boat and pushing it backward, then it's going to slow down or go backward. So the second key to this is that the sail is not just a parachute that's kind of dragging us straight down with the wind, because if that were the case, we would now have a boat that can travel dead downwind and could probably travel very close to perpendicular to the wind, but could still not make any progress upwind, because we haven't yet created a force that has any upwind component to it. So the next piece of the puzzle is a sail that can do something other than direct downwind, just kind of dragging us downwind. And so that's where these sails that essentially operate like an airfoil. Typically, a sail is made of fabric, and that fabric, again, is stretched between the mast and the boom in a triangular shape. But there's a little more to it. Often the fabric is not just kind of a flat kind of piece of cloth. It's actually cut and shaped so that when the wind presses against it and fills the sail, it actually takes a curved shape, a lot like a single surface of an airplane wing. Think the upper curved surface of an airplane wing, which is another airfoil. And so that curved wing shape is able to more efficiently take the flow of the wind from the leading edge, where it's attached to the mast, kind of forward on the boat, along that sailcloth to the trailing edge, following that curve. Essentially, that wind gets its direction changed. The air that's near the sail is affected by the sail. It changes the direction of that air, directing it more towards the back of the boat, and that creates a lift force. Now, it's not lifting you up in the air like an airplane wing, but it's lifting you to the forward and to the side in the direction that that sail's curvature is facing. And so there's also a drag component to this, as with any airfoil, but this allows us to create a force that has at least a partial upwind component, the lift portion of that force. And so the combination of that upwind component of the lift force created by the sail and the boat's shape in the water, like that ice skate, designing it to select the forward component of that force for motion and resist the sideways component, the combination of those two factors allow the boat to make progress upwind on a diagonal, essentially. And that's a lot to take in, so feel free to dig in.
Yeah. So you're not only redirecting some of the wind in a different direction to create that equal and opposite kind of thrust.
Yep.
But you're also using some of the Bernoulli principle a little bit, all the way. Man, see, and the reason I mentioned the ice skate thing earlier is I believe I've seen a visual that may have actually misled my intuition on this.
Okay.
And the visual, it was an ice skate visual where imagine instead of an ice skate, you have something a little bit longer, like a ski,
okay,
sitting on snow. And you take a stick and you approach it from a 45-degree angle, and you push on that ski just directly into it with a 45-degree angle, the ski might actually move backwards from what you would expect because it's kind of like getting out of the way of the stick.
Okay.
Have you seen this? And is this just an incorrect mental model?
Yeah, I'm actually having a really hard time picturing
I
this
know.
construct. So no, it's not intuitive to me yet.
Okay. I'm going to have to table that one then because I think maybe I'll link a video in the show notes or something and we'll figure it out.
Sounds good. Yeah, because there's some other assumptions like that we're pushing on kind of the center of pressure of the object so that it doesn't just pivot in one direction or the other.
Right.
And that we're applying the force straight through as opposed to any kind of offset on the stick itself, that we're imparting the force with. So I think
the important takeaway here is that the forces involved in sailing are like highly counterintuitive, in my opinion. If you just look at a sailboat out on the water, you think you got it, and you've never really studied it. You probably didn't get it.
Right.
Right. It's really weird.
Yeah, there's more to it. I mean, they're both simple, but also they're really subtle in how they're how they work. And to me, I feel like there's got to be a better way to kind of, and maybe visuals might help too. To understand how this sail can select, can provide lift that has some amount of into the wind component to it. And I guess if you were to picture a boat that had the wind coming straight from the side. So again, if the boat is if the boat's bow, the front of the boat is pointed towards 12 o'clock on the clock, imagine that this wind is coming from the 9 o'clock. It's coming straight from the side. And so if we just put up our parachute type sail, it's going to pull us sideways. Our keel's going to resist that. We're going to kind of drift clumsily down, downwind. It's not going to be any good. But if you put this triangular sail up and you set the sail so that, again, the leading edge of the sail is attached to the mast in the center of the boat, and put the trailing edge of the sail kind of out the back corner of the boat, sort of a 45-degree angle relative to the boat itself. Now you can picture the wind coming in at 9 o'clock, and it hits this sail and it's redirected, and the wind, instead of exiting the boat's area at 3 o'clock, the wind's actually exiting more at like 4:30. And so we've turned that wind. And so if you picture the net change in the direction and velocity of that wind, it was coming in at it was coming in at 9. It's leaving at 4:30. And so if you were to plot the direction of force required to make that change, I should have drawn this, but that direction of force is going to be over in like the 2 o'clock range. So we're going to be pushing the boat towards 2 o'clock. And by pushing it towards 2 o'clock, then our keel is going to select the 12 o'clock direction, ignoring, the 3 o'clock sideways force. And so now we're moving, perpendicular to the wind. So the wind's coming in from 9, we're moving at 12. Well, now imagine we turn the boat a little bit into the wind. And so the wind is coming in at 10 o'clock. And you do the exact same thing. And now you're going forward at 12 o'clock. The wind's coming in at 10. You've actually started going upwind. And again, you can kind of walk this up until you're at about 45 degrees. And the problem trying to get closer than 45 degrees to the wind is that there's less angle you can turn the wind and still gain a force from it. Like you could propel it to straight back, to your 6 o'clock. And if it's coming in at the 10:30, there isn't that much angle to change, which means you can't extract as much momentum from it. You're also, because you're going into the wind, as you gain speed, essentially the wind turns more and more into a headwind as you add your boat speed to the base wind, and you get that relative wind that's moving closer to the 12 o'clock, which gives you less room to turn it and more friction to overcome due to the wind you're going through.
Got it.
So it does work.
So cool. Yeah. Oh, yeah. I guess it does.
Surprise. And it works even
surprise.
And it works even better with lower drag. So like an ice boat can go faster and can probably go even more upwind than, say, a conventional boat in water. Mm-hmm.
Yeah. Wow, that's just incredible. Honestly, I think the first time I heard you talking about this in our last episode about how the wind is actually being rerouted, that was a totally new concept for me. And I would have thought at my old age that I would have understood that by now. Apparently not. All right. There is a term for this,
Yes.
right? Where you make your way upwind, because you can't, if you're going somewhere and the wind is coming from that place.
Yep.
You can't just go straight there, obviously.
That's right.
But you can go at an angle.
Yep.
And you can change angles repeatedly to get there. This is a concept, right?
Absolutely.
Kind of a navigational
yep.
technique.
And it's called tacking. And so, again, let's say by default we want to travel straight into the wind, and we can't do that with this construct. So we can go 45 degrees off center from straight up wind. And so we would go on one diagonal for a period of time. And then we would periodically switch to the other diagonal. So we kind of zigzag our way upwind. And each time we turn a sailboat, and we turn it so that we pass through that straight upwind point, and then we cross over to where the wind was coming, say, from the left side of the boat, and now it's coming from the right side of the boat. That's called tacking. And so a tack is that type of turn when we cross through the straight upwind point onto the other diagonal. And so,
and when you do that turn, you got to swing the sail to the other side of the boat, right?
Yep. Yeah. So if that
with the boom, and this is another reason it's called a boom, because if you're there,
that's what happens to your
when
head
you do that,
if you don't duck.
Yes.
Yeah, exactly. So yeah, and typically there's controls for all of this, and usually a boat will have a set of lines that they often, what we might call colloquially a rope. Is typically called a line, technically, and it's down to the way it's woven versus twisted. And so there's a line called a main sheet for your main sail that controls. Essentially it's attached to the boom and usually attached to a pulley or some type of winch on the boat, so that you can use that to allow the wind to push the sail on the boom further outboard, or you can use the line to pull it more inboard. So you can set it for the optimal angle relative to the wind and get the maximum benefit from it. And then as you tack and the wind begins to come over the other side of the boat, typically the wind will blow onto the other side of the sail and just push it across the boat to the other side. And again, if it's a small boat, you kind of got to stay out of the way. If it's a big boat, usually that boom is set high enough that it's going to pass over your head. And then that main sheet is going to catch it on the other side and hold it in that position, and then you can adjust it from there. And the term for adjusting that sail is trimming the sail, choosing exactly the right angle to the wind in order to gain the maximum benefit.
Awesome.
And if you're going downwind and you cross through the directly downwind point of sail from side to side, that's called a jibe, or jibing if you're going back and forth. So tacks are into the wind, jibes are away from the wind.
Okay. All these words.
Yes. Yeah, we won't do all the jargon, but there is plenty of it in the history of sailing.
It's amazing that the sheet is not the sail. The sheet is a line, which is a rope
attached to the sail. That's right. Everything is
that controls the sail.
Everything is one word different than what you would think it would be. Yeah.
Yes. It's like a cesarean shift. I think that's what that's called. Of all the jargon, they just shifted them down a few words.
Yeah.
That's what we get. All right. Okay. Well, I think we've pretty much got a complete and total understanding of navigation and direction finding.
Excellent.
Where do we go from here?
A couple options. One is we can talk about some of the ways to break these rules and optimize this construct. The other is, I know you'd expressed in the past some interest in racing and some of the tactics and constructs that are used for sailboat racing. So I guess, what sounds interesting to you?
Let's do optimizations. Let's talk about how to make a sailboat go faster.
Okay.
And what are some of the things that make a sailboat slow down? And I don't mean braking. I just mean what are the obstacles to speed?
Right. Yeah. What are the key limitations? Because if you identify the limitations, those end up being the opportunities for optimization. So maybe one of the first ones to talk about is the speed of the boat itself in the water, and this comes down to the shape and weight of the boat. And so if we start with keel boats, which are big, heavy boats that have a massive weight hanging beneath the boat in the water, so that as you tip the boat over, the weight wants to tip the boat back upright. You need to have a buoyant hull that can float all of that weight. and the shape of that hull is going to dictate how fast that boat can go. And so if you think of like a motorboat, and as you start a motorboat moving, if it's a powerful one, at first it kind of feels like it's pushing water out of the way. But then over time, as you gain speed, if it's a lightweight and a powerful boat, it starts to plane on the water, where it's more skimming on the top of the water. And so it's being held aloft. I mean, it's not sinking to the bottom of the lake. And the reason it's being held aloft initially was due to buoyancy from its displacement. So the weight of the boat was displacing an equal weight of water. But as it's moving faster and it starts to plane, then it's being held aloft more by like that Newtonian interaction of equal and opposite reaction, which is the boat's hull is dynamically pushing particles of water down, and so they resist that change of momentum, and they're holding the boat kind of up higher. And so that's called planing. And so like an extreme version of this would be like a surfboard or a wakeboard that might sink under the body weight of the rider, but once they have enough speed, it can skim on the surface. And historically, sailboats couldn't do that because they were so heavy and they didn't have enough power. They don't have a motor, you've just got the sail providing power. And so
is it because they couldn't get going fast enough? Is that what stopped them?
Yeah, so to plane, you need to be able to go fast enough that essentially you're interacting with enough particles of water over time quickly enough, pushing each of them down a little bit to have enough total force to hold the boat up higher. And so that's a function of the weight of the object and its speed. And so sailboats couldn't do either of that in their original form. And so we'll talk a little bit about what it takes to make a sailboat plane in a second, but let's talk about displacement-based sailing first, which is where you're relying on the buoyancy of the hull itself. And so if you're relying on the buoyancy of the hull itself, then you tend to get these shapes that are very kind of torpedo-shaped. So a rounded or kind of sharp front and a relatively skinny kind of elliptical hull, and then often a tapered stern at the back of the boat as well. And the reason for that is to make it sort of as kind of slippery or efficient through the water as it can be. And there ends up being a very important limitation when you do that. And that is you start to push a boat like that shape through the water with the sail. And as it gains speed, it starts to form waves. And so the bow or the front of the boat, as it is pressing through the water, forms a wave. It's pushing some water forward into the side. And so there will be a crest or a high point of that wave at the front of the boat called the bow wave. And then if you looked along the side of the boat...
It's kind of a bulge in the water ahead of the boat?
That's right, a bulge in the water at the front of the boat. And if you were to look along the hull of the boat at the waterline, you would see then the waterline kind of starts to dip down because that wave goes from a crest down to a trough. And then it starts to climb back up towards the stern of the boat, the back of the boat. And when the boat's going slowly, picture like little ripples coming off of it, you'll see a series of these waves going down the side of the hull of the boat. As the boat gains speed, the boat essentially is moving faster in the water, and as a result, this wave starts to stretch out along the side of the boat until you get to the point where the boat is going essentially the same speed as the wave itself. And so you have the peak, that bulge at the front of the boat, a trough of that wave along the center line of the boat, and then the next peak of that same wave is at the stern of the boat. And it turns out that wave actually kind of helps push the stern a little bit along and kind of balances out the force at the front that's creating the bow wave. And so you sort of get this cancellation effect where the boat is like riding in the trough of its own wave. It's being helped along by the back side of the wave, and it's being resisted by the front side of the wave.
Is that because the wave curls around the back side following the curvature of the boat and then ends up having some forward component in the motion of the water?
Yeah, and even just the angle. There's forward component to the pressure the water's applying to the hull because it's kind of it's coming up.
Oh, yes.
Up the stern.
And the hull gets narrower at the stern, right?
Yeah.
Is it kind of a pinching motion?
And that pinching helps to ensure there isn't like a cavity at the back that creates like this vacuum or this extra drag. But yeah, it kind of helps it to carry forward. And so it's a pretty efficient speed for the boat to go at. And it's what's called the hull speed of the boat, which is it's defined by the shape and the length of the hull. And so a longer
So
boat.
you're okay.
Go
So
ahead.
I just want to clarify something there.
Yep.
So earlier you mentioned that this trough, kind of the peak and trough of the wave as it goes along the edge of the boat, uh, coincides with the length of the boat, but not necessarily. That coinciding only happens at certain
That's
speeds,
right.
right?
Given the size of
And
the boat.
presumably multiples of those speeds.
Yeah, so there's a speed where maybe you get two wavelengths or like a full, yeah, like two, like a peak and a trough and a peak in the middle of the boat and a trough and then a peak at the stern of the boat. And then
Mm-hmm.
as you go faster, then there's going to be a speed where essentially the boat is riding entirely in the trough of one wavelength, from peak to peak.
Yeah.
And if you try to push the boat much faster than that, as it starts to accelerate from there, the wavelength of that water wave is longer than the hull of the boat, which means the back of the boat is no longer receiving the benefit of that rising edge
Mm-hmm.
of the wave. And so you have a little bit less of that pressure and force in the back of the boat. Meanwhile, the bow of the boat, the front, is still trying to climb and push that bow wave. And it ends up taking
Yeah.
a lot more energy to go faster than that single wavelength speed than it took to maintain that single wavelength speed. And so
Interesting.
they call that the hull speed of the boat, which was the natural speed that the hull or the body of the boat wanted to maintain in the water. And so,
Which I presume that the hull speed varies a lot based on the shape of the boat, the length of the boat.
yes,
Maybe those are the only two factors.
yeah,
And I'm thinking about this now in the limit. So what if you had a really long boat? Does that mean that its hull speed would have to be really, really fast in order to get that wavelength, the water to make its way all the way to the back and then coincide with the stern?
yes, exactly. And so, one way to make a faster sailboat is to make it longer, and then to provide enough power in the sails to achieve that resultant longer hull speed. And so
Got
and
it.
so there's an incentive to essentially making longer boats. And when we talk a little bit about racing, that can be one of the key differentiators between different classes of sailboats. Ones that would be competitive with each other, is based on their, the length of their hull, in the water, because there's just a
Yes.
fundamental advantage to the longer boat.
That is so interesting. So I had heard that the length of a sailboat, the longer boats can go faster. I did not realize it was because of this wave effect. That is so cool.
Yep. And again, that mainly applies when the boat is just floating buoyantly in the water. And so there's other ways to overcome the hull speed. And one of them is to create a boat that is lightweight enough, which means maybe you had to dispense with the keel and use some other tricks to keep it from, to keep it upright, like having, for example, a catamaran where you have hulls that are out to the side, and so they can provide that righting force when you try to push to the side, or maybe some hydrofoil, something in the water that can provide a lifting force out to the side of the boat so that it can keep it upright. And if you play some tricks like that, and you can create a boat that's lighter weight, then you can potentially have more of a flattened bottom on the boat. And if you get enough speed, it can start to plane just like one of those motor boats can. And so you have to have enough sail area to provide enough force to generate enough velocity that the boat begins to skim on the water instead of displacing water. And at that point, you're no longer bound by the limit of that single wave trough, because you've essentially climbed out of that single wave, and so now you can go faster than the hull speed.
So at that point, do you actually have a new hull speed that takes into account a much smaller area of the boat that's actually in contact with the water?
You would, except you're not relying on that rising edge of the backside of the wave to press you forward anymore. It's sort of you switch into kind of a totally different regime where now your speed is going to be mainly a function of just of the drag and the resistance in the water itself, as opposed to the resistance being due to pushing that wave of water. It's now the resistance is due to the friction and kind of skimming over the water.
Got it. Wow. Okay.
And so if you picture like a surfer, they're planing.
Oh,
They're
yeah.
skimming across the top. They're not kind of plowing through and displacing water as they go.
Is this the same physical phenomenon that allows rock skipping to take place?
I think so. Yeah, because the rock is obviously heavier than water, so it's for sure not displacement based unless it's like pumice or something. And so the way it kind of smacks the water and skims off is going to be, yeah, a momentum transfer of, the rock pressing down on the water equal and opposite, pressing up on the rock enough to even bounce the water or rock up. And like if you skip like a bigger rock, you'll kind of see it kind of like slide on the surface and kind of plow through the water before it sinks down, and that's
yeah. Toward the end, after it gets out of skipping mode and starts hitting the water, you actually see that same wave effect.
Yep.
And the rock has a hull speed.
Yeah, ultimately it does, and then it slows down.
But it doesn't have enough buoyancy to actually stay afloat. So,
that's right.
That's really cool.
Okay, so one way to optimize away from hull speed then is to make the boat plane, and now your speed is going to be more limited by the amount of surface area that the water is in contact with, because that's going to, again, provide like drag. There's also going to be a certain amount of resistance due to you're pushing the water that you're planing on. You're pushing it mostly down, which is what's pushing you up and lifting the boat out of the water. But there's a little bit of pushing it forward as well. Imagine like your hand kind of sliding along the water with you're pushing the water forward as well as down a little bit. So there's a little resistance from that. And then, of course, there's going to be, air resistance. But the next way to reduce the resistance of the water is to lift more of the boat out of the water. And so we talked last time a little bit about hydrofoils, which essentially are a wing in the water. And that wing can, over time, as you gain speed, it can generate lift in the water and essentially lift the entire hull of the boat out of the water, or maybe most of it out of the water.
Mm-hmm.
And now you have much less of that water-induced drag. The hydrofoil wing is much more efficient in terms of its lift to drag ratio. And so there are a number of modern sailboat designs that utilize hydrofoils at speed to lift some or all of the hull out of the water. And so now you've overcome that hull speed limitation. You've even overcome the water-based drag of a planing configuration, and you have very little drag, which means you can go much faster in lighter wind with less sail area. And so it begins to behave more and more like that ice skate that we talked about, and less like what we're used to thinking of in terms of the boat's performance in the water.
Wow. Okay. Incredible. All right. I'm sure there's more optimization, though. We just talked about hull and hull speed.
Yep.
What else?
What else? Let's see. So we talked about keels, and again, you can replace them with lighter weight structures. We talked about dagger boards last time. Just it's a lot like a keel, but it doesn't have that big weight on the bottom. People have experimented with a rigid wing instead of a fabric sail. The fabric is a little, because it's more flexible, it maybe isn't as perfectly shaped at all times. And so a manufactured wing, kind of like a lightweight, like a glider wing, that you use on a like an airplane, can be very efficient, but they're also very unwieldy. And so there was a racing series, the America's Cup a few years ago, where they used wings instead of fabric sails, and they had to have like a crane that would place the wing on the boat and then take it off when they're done. Whereas a fabric sail, you can just like raise and lower and roll up.
Right. Mm-hmm.
But the result was that these boats were extremely efficient, and in very light wind, they could generate enough power to lift the boats up onto hydrofoils, and then they could ride very light breezes on foil, and they could go very fast. So they were extremely efficient, highly optimized, also extremely impractical.
Yeah, so you're saying have these fallen out of favor?
Yeah, so the America's Cup is kind of a special thing, where whoever wins it, and it's a traveling trophy, and there's a long history between yacht clubs, but whoever wins it then gets to make the rules for the next time it will be contested. When a team in the US, I think is based in San Francisco, won, they said, we want to push the technology to the extreme. So we're going to define this class of boat that's going to be a catamaran. They were huge catamarans. They had hydrofoils. They had these wing-based sails, and then they raced them in the San Francisco Bay. And then the next team essentially said we're going to take some of those ideas, but we're gonna reduce the scope. We're going to go back to monohulls. Foils are still in, so we can make these monohulls really efficient. Monohull being a single hull, not the two hulls of a catamaran. And we'll use high efficiency fabric sails, or at least flexible sails that can be rolled up and managed more sustainably and don't require all the infrastructure to of cranes and equipment to load the boat and the sails on and off the water.
Got it. Wow. And is this these rigid sails? Is this the same kind of sail that windsurfers use?
So a windsurfing sail tends to be very taut, but it's not fully rigid. So that tends to be like a single piece of fabric or mylar, some type of plastic. No, these would have been, I guess they were think more like, actually a lot like an RC airplane wing, where they had a set of ribs and then had maybe a top and bottom surface of mylar, but they're symmetric. And then kind of like an airplane wing that has control surfaces on the trailing edge. They had a hinge and kind of like flaps or ailerons, like a control surface that could change the curvature, the camber of the wing dynamically. And if I remember right, they actually had 3 sections of controllability, like a top and a middle and a bottom, because you'll have different speed wind at the top, the middle, and the bottom. And so that allowed the sailors to optimize the whole profile, or at least,
oh my goodness.
It's pretty ridiculous.
Oh, that's amazing. That is amazing. Are we talking like a 2x speed increase or like a 5% speed increase with that kind of technology?
Like a multiple. So the difference between getting the boat up on foil or not easily doubles the speed of the boat. And so the racing ended up being all about who could figure out how to get the boat up on foil and then stay there as they traversed the entire race course. And the teams that were most effective at that just, totally dominated the competition.
That's amazing. I can't imagine. I'm definitely going to check out some videos of that.
Yeah, it's well worth it. And so then the other thing that's crazy is when you make a boat that's that efficient. So it's up on a foil, say, which means that it has very little drag in the water, and it has an efficient enough sail. In this case, these wings, but even a highly efficient flexible sail can do this. And now, instead of going dead downwind, if your goal was to go straight downwind, you're actually better off jibing on diagonals relative to straight downwind. So maybe 45 degrees, to the left of downwind, and then jibe through 45 degrees to the right of downwind. Because again, as long as you have some angle to the wind coming from the side of the boat, and you can bend that wind at least incrementally so that it leaves more toward the back of the boat, that can impart some amount of a forward force. And if that overcomes the current frictions you're experiencing, you will accelerate the boat.
Amazing.
And so counterintuitively, these boats, by kind of diagonaling downwind, it's like cutting through a crowd at a mall or something. Like they were able to move through the wind faster than the wind was propagating itself. And so, if you were to let go of a balloon or a parachute at the same time as one of these sailboats went past, the sailboat would get to the finish line dead downwind faster than that floating object in the wind would get to the finish line.
Even though it's probably traveling 30-40% more distance.
Yeah, exactly. Yeah, maybe up to double the distance in practical terms, but going so much faster.
My goodness. So tell me, what kind of speeds are we talking about here for the fastest sailboats in the world?
Some of these boats are in the 40 mile an hour kind of range, and probably the fastest ones probably get up into maybe the 50-60 mile an hour range for at least some period of time. So they're really moving.
Incredible. And then if they come off foil, it's like, what are they capped at, like 30?
Yeah, it depends on the shape of the boat, and there are some that are kind of highly optimized to be able to plane and maybe can do that type of speeds. And then, a more typical speeds would be in the teens to 20s range for a relatively fast traveling sailboat.
Amazing. Wow. Okay. Well, should we take a few more minutes to talk about racing? We've touched on racing a little bit here, but I know there's more. Or should we do a part 3?
I think let's try talk for a couple minutes, and maybe we'll be, that might allow us to be done with this topic, because I think we have a lot of fun ideas to go to next.
Listen, if we spend a few more minutes and I'm not satisfied or I'm hungry, we're going to have to do a part 3.
I'm totally okay with that. I have no problem with that. I think so. Yeah, let's do at least a teaser, and we'll see where it takes us.
So you already touched on this big event called the America's Cup. Is this by far the biggest sailing event or the most well-known sailing event in the world?
It's one of the most prestigious. There are a number of high prestige events, but it's sort of the
It's kind of the World Cup of sailboat racing.
Yeah, I would say so. It's yeah, exactly. It's at the extreme end in terms of it's not even on a dedicated schedule. They kind of make up fresh rules every time. Yeah, so it's kind of the least structured and most extreme, I guess.
That is very interesting that the winner each event. So you're saying it's not even a consistent repeating schedule.
Right.
And the winner of the previous event gets to make the rules for the next event.
Yes.
What other sport is like, listen, I won the PGA Tour. Next year, we're going to be playing with pool cues. Like
Exactly. Yeah. Yeah. I mean, again, we could look up the history. I don't have it off the top of my head, but I think it was probably a yacht club over in England and a yacht club probably in the East Coast of the U.S. That had this initial challenge of, hey, we're going to see who can build the best boat and win this race. And part of that, the format of that challenge was whoever wins gets to make the rules next time. And then there's this process of challenging them. So it's like they get the trophy and then somebody has to challenge them and say, hey, we want to try to oust you as the holder of this trophy. And then they set the rules, and then other challengers in some cases are allowed to enter as well. So the last few iterations of the America's Cup have had kind of a preliminary series that allows multiple teams to design and build and crew a boat to whatever specification they've agreed to. And then they'll kind of do a tournament to see who gets to be the official challenger that then does the sort of the one-on-one with the current trophy holder, and then whoever wins that takes it for next time.
Okay, amazing. So last episode we touched on some of the strategies of sailboat racing, and I'd love to do that a little more. One of the things you mentioned was that you can strategically place your boat in front of another boat such that you mess up the wind for them. So they no longer have a nice smooth flow of wind. It's turbulent. It's got eddies.
Yep.
Tell me a little bit about that strategy there. And also, like, there are some rules about when you can and can't cut in front of other boats. So help me understand that.
Yeah. So there's really two things. One of them are the aerodynamics themselves, and then the other are the right-of-way rules. And so essentially, in boating, just like driving on the road, there are rules about who has to yield to whom. And so you can exploit those rules to your advantage. Imagine, so in racing, in auto racing is typically on a closed course, but imagine if you were racing on city streets and you had stoplights and stop signs, that you had to obey. You might be able to use like the yielding to the driver to your right in the US type of rule, to win some advantages. And there's similar things on the water. So I guess first, because you mentioned the physics side of it, because the sail is disrupting and changing the flow of the wind, if you end up in what's called the wind shadow, essentially downwind of another boat, there's much less effective airflow to make use of. And so the power available in your sail, if you're in that downwind wind shadow, is greatly reduced. A boat that can get into an upwind advantaged position where you're essentially casting your disrupted airflow onto the boat downwind from you, can maintain that position and make it extremely difficult for the downwind boat to ever catch up. And so there are a couple of different types of racing. One type of racing where you have a lot of boats all racing together is called fleet racing. And so in that case, you're just trying to be ahead of the pack. And again, the boats at the front are going to have an advantage over those behind. The other type in like the America's Cup is called match racing, where it's one-on-one. And there it becomes very tactical, because if you can gain that position of advantage, you can kind of maintain it for the rest of the race. It's almost impossible to overcome. The second key mechanism are those right-of-way rules. For example, a boat that is typically clear ahead has right-of-way over boats that are behind them. And so if you can stay clear ahead, then you can sort of go where you want in a lot of cases and kind of block somebody behind you, forcing them to go around. Also, there are two key directions. So if you are traveling where the wind is coming from your right, you are on what's called starboard tack. The wind is coming from the right side of the boat, which is the starboard side of the boat, another piece of jargon. And you automatically have right of way over any boat that has the wind coming from their left, that's on port tack. And this is determined by where their sail is relative to the back of their boat. And so you can use that to your advantage. Like if I'm on starboard tack and I'm coming up on a boat that's on port tack, even if they would otherwise kind of be ahead of me, but if I can show that they're going to impede my progress, they're actually forced to yield. The port tack boat must yield to the starboard tack boat. And I'll say, when you get into that situation and you're on port tack and you're forced to yield, it really isn't that satisfying. It feels pretty wrong. But because everybody understands the rule and you take it into account, it's a key part of strategy. And there are other strategies as you're approaching like a buoy that you're going to try to make a turn around. Maybe it's on a closed course where you have to go around a series of buoys. Boats that have what's called an inside overlap, so they're trying to squeeze between you and the buoy. Often they have the right of way to make that maneuver if they have achieved enough overlap with your boat within a certain distance. And so they can force you to deviate from course in order to give them room. There end up being a lot of tactics around becoming in an advantage position where you can force the other boat to yield and take a worse path, which might then put them in your wind shadow, for example, allowing you to succeed. Being fast and being in the right place are important, but so are these tactics.
I love the term wind shadow. It's like downwind, or I guess,
downwind.
Downstream of the wind that you are projecting off of your boat is your wind shadow.
Exactly.
That's so cool.
Okay, so I guess, any other questions, or did we cover this one?
Oh, man. I feel like I know everything I need to know about sailing now. I'm just ready to go hop in a boat, maybe a dinghy.
That'd be a good starting place.
Oh, it's so cool. At some point, we're going to have to do more aeronautical stuff.
Yes.
One of my goals, anyway, I think will be that if we can get to a point where it's clear why the word aeronautical has both water and air terminology baked into it, why these are basically the same. Yeah. They refer to a lot of the same dynamics and same physics. I think that'll be a really fun day.
Yep. Yeah, that sounds awesome.
Well, I think you've left me not craving more on sailing, so I think we can call this a successful series of 2. We don't need to go to a trilogy.
Excellent.
What parting words do you have how about this? Like, in just a few moments, what would you advise people if they want to get into sailing? How do they start?
Yeah, that's a great question. Honestly, finding some local instruction, and it might be surprising, you don't need an ocean to go sailing. A small lake can be a great place, and anywhere that there is a body of water like that, there are probably at least a few people who are into sailing. And if you can find them, and just start by seeing if you can go out with them and just observe, and then maybe start to learn something. There's enough subtlety to it, and there are also some ways it can go horribly wrong, or even just maybe comically wrong, but still not necessarily in a fun way. that a little bit of help with someone who knows what they're doing can make a huge difference. And so that would be my advice: is find some locals that are into it. And
if you live in the middle of a desert with no water, I'm sorry, you're out of luck. I guess you can do kiteboarding or something instead. It's like very similar concepts.
Yep, it is. And honestly, kiteboarding is a type of sailing. Your sail is way out at the end of your lines instead of attached to the boat. If you've got hard-packed sand, there are land sailing organizations. I've seen that also done, like on the desert kind of lake beds where people go, do like land speed records for cars as well. I've done a little bit of sand sailing when we were in New Zealand. They called it blow karting, sort of a go-kart, because the wind is blowing it.
Oh, that's hilarious.
Blow karts.
I love that name so much.
And I think up in the upper Midwest, like in the Minnesota area, of course, have tons of lakes, but ice boating is a thing. I mean, you need to dress warmly, but you can go really fast on an ice boat as well. So liquid water, not strictly required, though that is the most common format.
Right. Solid water or sand, which is essentially water with harder particles. I don't know. Okay. Thank you, Shane. This was awesome. And this concludes episode 2 of Explainercast. We'll see you next time.